Hello. Today under classification of polymers, we shall see the last type, that is polymer type. So we have already gone through all these various types of classification of polymers based on the origin, the thermal response, the type of polymerization, the molecular characteristics. We've seen the four subclassifications, that is molecular weight, molecular shape, structure of the molecular chain, molecular configuration and tacticity. We have also seen crystallinity, and now we shall see the last type, that is polymer type. So how the polymers are classified as per the type or the applications that they are used in. Before that, we shall see what are the intra and the intermolecular forces that are there between the chains, so that we understand the polymer type in a better way. So intramolecular forces are forces that exist within a molecule. So within a molecule, whatever bonds are there, those are mostly covalent and ionic bonds. And intermolecular forces are forces that exist between different molecular chains. So we would be more interested in types of intermolecular bonding, because that is what we can really use during our processing, as well as understanding the polymer is better if we are able to understand the intermolecular bonds that are there, the various types, and their properties. So intermolecular force is an attractive force that is there between neighboring molecules. There are three types of intermolecular forces commonly found. That is permanent dipole-dipole. Then you have a hydrogen bond. Then you have van der Waals or the London dispersion forces, as they are called. All the above forces are weaker than the covalent or ionic bonds that bind the atoms and ions in a compound, but still they have some kind of hierarchy when it comes to the strength of these bonds between the molecular chains. So first we shall look at the hydrogen bonds. Both dipole-dipole bonds and hydrogen bonds are polar bonds. That is, a positive and negative charge is formed that attract the neighboring molecules. Um, so hydrogen bonds are much stronger than the permanent dipole-dipole bonds. They are just another form of dipole-dipole bonds. Hydrogen bonds are extra strong dipole-dipole bonds, one can say. So hydrogen bonds are categorized separately since they are found only between NH, OH, and FH. So if in a molecular chain one finds these atoms NH, OH, or FH, then one can be sure that there will be some kind of hydrogen bonding between the molecular chains. For hydrogen bonds to be formed between molecules, the molecules must have a bond between either NH, OH, or FH. So hydrogen bonds are strong because they are small. Since the hydrogen atom is small, so the bonds that they form are quite strong, and they are able to come closer to O, N, or F to form stronger bonds. So now we come to the next type, that is van der Waals and London dispersion force. So, van der Waals forces are weak forces that occur due to the temporary or permanent dipoles that are formed. They are also called dispersion forces. Van der Waals forces include London dispersion forces. In case of non-polar molecules, the molecule can have an instantaneous dipole. That is, it is a temporary dipole. An instantaneous dipole in one molecule may induce a dipole in the neighboring molecule. They are very weak, and they are also not the permanent types, they are short lived. Larger the molecule, higher is the attractive force. These forces can exist between any type of molecule over the entire surface. So they will normally you will find them in any kind of molecule, and that too over the entire surface. So usually this is the hierarchy. Covalent bonds are stronger than ionic. Ionic is stronger than hydrogen. Hydrogen is stronger than dipole-dipole. And last is the London dispersion, which is the weakest of these bonds. So now we can see the polymer type, which is based on application, how they are classified. So the first one is rubber, also known as elastomers, characterized by elasticity. Then comes the plastic. They are stronger than rubbers. They are rigid and dimensionally stable. Some plastics may be soft and flexible. Then comes the fibers, which are of interest to us as a textile technologist. They are the strongest of the three types, And then we can also see how polymers are used as coatings, adhesives, and as well as foams, and also in some film applications. So there are many different polymeric materials that are familiar to us and find a wide variety of applications. In fact, one way of classifying them is according to their end use. Depending on the properties, a particular polymer may be used in two or more of these application categories. For example, a plastic, if cross-linked and utilized above its glass transition temperature, may make a satisfactory elastomer. So, or a fiber material may be used as a plastic if it is not drawn into filaments. So, we come to the first type, that is a plastics. Polyethylene, polypropylene, polyvinyl chloride, polystyrene, and the fluorocarbons, epoxies, phenolics, and polyesters may all be classified as plastics. They have a wide variety of combination of properties. Some plastics are very rigid and brittle, others are flexible, exhibiting both elastic and plastic deformations when stressed, and sometimes experiencing considerable deformation before fracture. So polymers falling within this classification may have a degree of crystallinity, and all molecular structures and configurations, linear, branched, isotactic, are possible. So plastic materials may be either thermoplastic or thermosetting. So, however, to be considered plastic, linear or branched polymers must be used below their glass transition temperatures. If amorphous, or below the melting temperatures if they are semicrystalline in nature, or must be cross-linked enough to maintain the shape. So, this is about plastics. So applications of plastics are for applications in which optical transparency is critical. Polystyrene or polymethyl methacrylate are especially well suited. However, it is imperative that the material be highly amorphous, or if semi-crystalline, have very, very small crystallites. The fluorocarbons have a low coefficient of friction and are extremely resistant to attack by a host of chemicals even at relatively high temperatures. So they are used as coatings on non-stick cookwares, in bearings and bushings, and for high temperature electronic components also. So next we come to the rubbers or the elastomers. Natural rubbers is still used to a large degree because of its outstanding combination of desirable properties. However, the most important synthetic elastomer is SBR, which is used predominantly in automobile tires reinforced with carbon black. NBR, which is highly resistant to degradation and swelling, is another common synthetic elastomer. For many applications, example automobile tires, the mechanical properties of even vulcanized rubber are not satisfactory in terms of tensile strength, abrasion, and tear resistance and stiffness. So these characteristics may be further improved by additives such as carbon black. So there are other elastomers like silicone. The silicone elastomers possess a high degree of flexibility at low temperatures and yet are stable to temperatures as high as 250 degrees Celsius. So in addition, they are resistant to weathering and lubricating oils, which make them particularly desirable for application in automobile engine compartments. Also, the property of biocompatibility is there, which is another asset, and therefore they are often employed in medical applications such as blood tubings. So next we come to fiber forming polymers. So one must remember that not all polymers are fiber forming. One cannot form fibers from all polymers. So there are certain requirements of the polymer so that they can be transformed into a fiber. So polymer must be linear and regular with no bulky side groups in the chain. There must be intermolecular attraction between the molecular chains, and ideally there must be some inflexibility in the molecular chains. So required characteristics a little bit in detail we shall see. The fiber polymers are capable of being drawn into long filaments having at least 100:1 length to diameter ratio. Most commercial fiber polymers are used in textile industry, being woven or knit into a cloth or a fabric. In addition, the aramid fibers are employed in composite materials. They must have a high tensile strength over a relatively wide temperature range and a high modulus of elasticity as well as abrasion resistance. These properties are governed by the chemistry of the polymer chain and also by the fiber drawing process, which we shall see in detail as we see each and every fiber later on. So some of the more other characteristics required to form a fiber is the molecular weight. The molecular weight of the fiber material should be relatively high, or the molten material will be too weak and will break during the drawing process. Also, because the tensile strength increases with degree of crystallinity, the structure and the configuration of the chains should allow the production of highly crystalline polymer. That translates into a requirement for linear and unbranched chains that are symmetrical and have regular repeat units. Polar groups in the polymer also improve the fiber forming properties by increasing both crystallinity as well as the intermolecular forces between the chains. So, convenience in washing and maintaining the clothing depends primarily on the thermal properties of the fiber polymer, that is, its melting and glass transition temperature. Furthermore, fiber polymers must exhibit chemical stability to a rather extensive variety of environments, including acids, bases, bleaches, dry cleaning solvents, as well as sunlight. In addition, they must be relatively non flammable and amenable to drying. So next we come to the classification of coatings, where coatings are frequently applied to the surface of materials to serve one or more of the following functions: to protect the item from the environment that may produce corrosive or deteriorative reactions, to improve the item's appearance sometimes, to provide electrical insulation. Many of these ingredients in the coating materials are polymers, most of which are organic in origin. These organic coatings fall into several different classifications like paint, varnish, enamel, lacquer, and shellac. Many common coatings are latexes. A latex is a stable suspension of small insoluble polymer particles dispersed in water. So these materials have become increasingly popular because they don't contain large quantities of organic solvents that are emitted into the environment. That is, they have low volatile organic compounds, VOC emissions. VOC emissions react in the atmosphere to produce smog, and that is why they are undesirable. Large users of coatings such as automobile manufacturers continue to reduce their VOC emissions to comply with environmental regulations. So next classification we come to adhesives, where polymer may be used as an adhesive. An adhesive is a substance used to bond together the surfaces of two solid materials. There are two types of bonding mechanism, mechanical or chemical. In mechanical bonding, there is actual penetration of the adhesive into the surface pores and crevices. Chemical bonding involves intermolecular forces between the adhesive and the adherent, which forces may be covalent or van der Waals. The degree of van der Waals bonding is enhanced when the adhesive material contains polar bonds. So, although natural adhesive, that is animal glue, casein, starch, and rosin, are still used for many applications, a host of new adhesive materials based on synthetic polymers have been developed. These include polyurethane, polysiloxanes, that is silicones, epoxies, polyimides, acrylics, and rubber materials. So next we come to the application of films. Polymeric materials have found widespread use in the form of these thin films. Films have a thickness between 0.025 to 0.125 mm and are fabricated and used extensively as bags for packaging, food products, and other merchandise, as textile products, and in the host of other uses. So, important characteristics of the materials produced and used as films include low density, high degree of flexibility, high tensile and tear strength, resistance to attack by moisture and other chemicals, and low permeability to some gases, especially water vapor. So, these are some of the characteristics that one would look at if somebody is using a polymer as a film. Some of the polymers that meet these criteria are manufactured in film form are polyethylene, polypropylene, cellophane, and cellulose acetate. So the next classification we come to is as foams. So foams are plastic materials that contain a relatively high volume percentage of small pores and trapped gas bubbles. Both thermoplastic as well as thermosetting materials are used as foams. So some of the examples are polyurethane, rubber, polystyrene, and polyvinyl chloride foams are commonly used as cushions in automobiles and furniture, as well as in packaging and thermal insulation. So we have seen the polymer type, how they are classified into various categories, and that was the last uh, kind of classification of polymers. So with this we close the session. Thank you.